All right, welcome back everybody. So today's lesson is about data. It's really our first introduction into working with data as part of our computer programs. We also get into one of the distinctive features of Java, particularly if you're coming from a programming background that was largely Python based, which some people, Python is a popular introductory programming language now. Some people learn that first. So one of the things that you'll notice that's different about Java is that we have to use types when we work with data in Java. When we declare variables, we need to also tell our program or indicate in the program itself what type of data those variables are going to store. All right, so let's get started. Again, these walkthroughs are not intended to, they're not intended to replace your interaction with the lesson content. It's a chance for me to kind of go over some things. I'll take some questions. Today I have the chat stream available on the YouTube video. One thing I just want to point out is that when you guys are welcome to chat in that chat stream. We also have I think we have a chat available now on the forum for students as well. The problem with the chat feed is that it moves pretty quickly, and so when I'm focused kind of on trying to talk about stuff or go through something as part of the lesson, it can be difficult for me to see questions that are posted there. And so I still do have the lesson thread available on the forum. So if you go into the forum, the Fall 2020 category, there's a Fall 2020 lessons thread, and I'll be looking at that as well periodically. All right, so the first part of today's lesson code goes through how to declare and initialize variables in Java and starts introducing you to some of the syntax that's part of the language. Over the next few lessons, we're kind of doing a multi-part series on the basic building blocks of simple computer programs. So there are 3 or 4 things that computers are good at that we're going to start off introducing you to. One is they're good at storing data. Another thing they're good at is manipulating data, which we'll talk about tomorrow, different ways that you can modify and transform and do mathematical operations on the data that are stored in variables. Later in the week, we'll look at decision making, how to have a program make a choice between doing 1 or 2 things based on some information. And then next week, at the beginning of the week, we'll talk about repeating things. So taking a set of instructions in your computer program and repeating those instructions multiple times. And those together really comprise the basics of the basic building blocks of what we refer to as kind of imperative programming that we're going to use throughout the semester. On some level, you always have to be careful about saying that things are simple, because sometimes people interpret that as meaning, oh, if I don't get it, then I'm dumb or something like that. That's not what we mean. But computers at their core are pretty simple beings. They're only really capable of a couple of simple things. All right, so let's look at, let me go back and find this lesson. So again, this is the first part of this. We talked a little bit about how to declare variables. There are, and I'll sort of skip through this unless people have questions, of which you're welcome to ask. There are one important distinction that's a little tricky for people when they're getting started is this distinction between a variable and a literal. And trying to come up with good analogies for explaining that. So, a variable, sometimes people talk about it's like a container that you can put things in. It stores a value, and you can put a value into it by assigning a value to it, and you can also retrieve that value in a variety of different ways. So when we look at this example right here, let me run this piece of code. What's happening is on the first line, I'm storing, so I'm doing 3 things. I'm telling Java, hey, I'm going to use this variable in my program called I. You can call these variables whatever you want. And good variable naming is actually incredibly important. It's something that we will focus on in a variety of ways in this class. We'll talk about and we'll try to model good variable naming practice. Now, for these simple examples, it's hard to name the variables in an appropriate way because these pieces of code aren't doing anything. The best way to name a variable is in a way that indicates what it's trying to accomplish. And that's a good reminder for you as you go through your program of what the variable cat is here. You want to come say hi? Oh, yes you do. Do you like variables? I'm not sure. Okay, well, just stay up here on the desk. That way you can keep me company. So, we're doing three things. We're saying, well, because this code, again, it's not done in the context of anything. I is an OK variable name, but we can name this anything we want. We could say example, and then we'd have to print off the value of example. The code would work the same way. We can assign a different initial value to the variable, same thing. So on this line, we're declaring that we're going to use a variable in this program called example of type int. We assign initial value to it, and then on the second line in the program, we're actually retrieving the value. So when we print a variable, what we actually see displayed is the value that variable is storing. So that's an example of a variable. That variable can take on different values as the program runs, and usually when we declare a variable, we're doing so because we expect it to take on different values as the program runs. We're going to modify it later. We might and again, we'll talk about all the different ways or some of the different ways that we can modify variables in tomorrow's lesson. So that's a variable. A literal, on the other hand, is an actual value that appears in the program that does not change. It can't be assigned to, it just is. So for example, I can also print the value of a literal. So if I print 10, what you're going to see displayed is just the value 10. 10 isn't a variable, so I can't, do something like this. That doesn't make any sense, right? I can't assign a value to a literal. It's just it is the value that it is. It doesn't change, and it's not named and declared like a variable. So there's a variety of different types of literals that we use in our programs, depending on the kind of variable that we're using. Right, so this value here is an integer literal, the literal 12. There's some other examples of literals down here later in the lesson. So in Java, there are what we're talking about today are these building blocks, and maybe one thing I'll do in some of my walkthroughs is try to give you a little sense of kind of like where this goes. So one of the most powerful things that we can do with computers is manipulate data, and that's really what computers are for. They're for performing computations on data. So, when you record a screencast, when you, work in a spreadsheet application, when you analyze data using some sort of tool, what you're doing, in some cases implicitly, in other cases explicitly, is you're either creating or transforming data. And performing really what amounts to a computation. We always don't think about it that way. So when I'm recording something using a screencast recorder, for example, I don't necessarily think that as my computer performing a computation, but it actually is performing a computation because it's taking, the video that's being recorded and it's actually performing a bunch of different computations on it to be able to represent it as numbers, which is the only thing that a computer knows how to understand, and also to be able to store it, to be able to record information so that it can be played back later and things like this. But you might think, well, how do I represent all the data that computers are able to work with today, whether it's data about the human genome. I was just reading an article this morning about how they're doing genomic analysis to be able to trace the spread of the coronavirus, for example. So you can detect mutations in the virus itself, and you can use those mutations to determine, in this case, what they determined was that there was this particular conference that was held in February in Boston that ended up, seeding outbreaks all across the country, and they've been able to confirm that using genomic analysis. So that was all done on computers, right? How do you do that, right? In order to do that, you have to represent the data, the human genome, in some way that a computer can understand. So again, how would you do that? I love music. People do a lot with music on computers, recording, mastering, mixing. How do you do that? How do you represent music as something that a computer can understand? What does the representation of a spreadsheet look like that you might interact with? Or a novel that you might read on your Kindle, right? All of these are built up in Java, at least, from combinations of these really basic building blocks. So Java starts everything. Every type of data that you can work with in a Java program, and pretty much that includes everything, starts with these simple building blocks. And it turns out that all of those types of data that I just mentioned can be represented by either one or more and combinations of these very, very simple building blocks. Let me just pause for a minute. I'll check the comment thread about questions here. Okay, somebody added somebody in the comment there. That's sort of random. Let's see. Okay, does the cat know Java? No, the cat does not know Java. Sometimes she'll get on the keyboard and try to type, but as far as I can tell, there's no Java code that comes out. Maybe she programs in a different programming language. You never know. Maybe she knows Haskell. So I don't know. What language would a cat know? That's a good question. We can talk about that in the forum. All right. So and let's think about some of the ways that we might represent more complicated data. There's an example later in this about how we do one example of representation that's based on convention that I'll talk about in a minute. But how would we represent, I might get you guys thinking, and we'll talk about this more later, like how would you represent music as just a series of numbers? How would you represent the human genome as just a series of numbers? How do you represent a spreadsheet as just a series of numbers? How do you represent an image, right? Photo data, huge part of what computers are doing online, and a part of all the sort of exciting AI stuff that's going on right now, where we're training computers to be able to perform simple tasks like image classification, for example. How would you represent all the data that a self-driving car needs to intake is a series of numbers, right? Information about the world around it. So that's a case where the data that we're doing computations on actually has to include things like, where am I in the world? Is there a pedestrian crossing the street in front of me? What time of day is it? What's the weather like? All these different types of information. So how do you represent them? In Java, we start with these building blocks, and there's 8 of them. These are the 8 Java primitive types. So for the next few weeks, until we start to talk about how to build more complicated ways to represent data, what we're going to be doing is really working primarily with these primitive types. And then also, we'll talk next week about ways to represent data using series of these values in something called an array. But there are 8 primitive types that are available to you in Java. They're broken into 4 categories. So we have integer numbers, and 2 out of the 4 categories and 6 out of the 8 Java primitive types are numeric. The other 2 are very close to being numeric in ways that we'll talk about in a sec. So I've got 4 different ways of representing an integer, 2 different ways of representing a floating point number. That's a number that has a decimal point. 1 way of representing a truth value. That's a value that can either be true or false. It can only take on 2 values. And then 1 way of representing a character, a piece of character data. So I don't want to subsume the lesson content. So there's examples in here about why these exist and what they're for. But it turns out, again, as we start to talk later in the semester about how we build more complicated data types, we can actually represent everything in the world that computers work with as a combination of these types. And really, what it boils down to is being able to represent everything numerically. For computers, inside of a computer, if you could see inside of a computer, everything in there is a number, right? Everything is just a series of numbers, and those numbers determine how things happen. Those numbers represent data and store information, but there's all numbers. Computers think numerically. They process numerically. They operate numerically. And so one of the things that we've had to do in order to get them to do things for us is figure out ways of, again, taking something like a photo and figuring out, okay, well, this isn't a number, but is there a way that I can transform it into a series of numbers so that the computer can then work with it and use that information and process that information and do cool things like apply fun filters and stuff like that. All right, so let me talk and again, this sort of gets into the core thing of what types are for, and then I think to close out this walkthrough before I just sort of get into pure Q&A, I'll show you kind of an advanced Java feature that we may weave into some of the future lessons that's related to this. It's kind of fun. So, why do we have types in the Java programming language? There are programming languages that don't require that you provide type information. Let me actually, just for fun, let me see if I can find quickly just a little. Oh, these are so terrible. Okay. Thanks. All right. So I guess this is all right. Can you guys let me see if this is coming through? Okay. So here's a little Python playground, and let's see here. So let's just try something simple. I haven't used Python for a while, so I want to make sure that this is going to work. So let's try printing hello world. This is hello world in Python, and it works. Okay. So let me show you something here. So in Python, I can just do something like this. So this is a variable. I've declared a variable called I. Let's print the value of I. Make sure that this works. And so at this point in my program, I've told Python that I'm going to use a variable called I, and I've set it to 10. And now over here, I can do something like this. I think it's capitalized in Python, right? All right. And I can print I. And I'm going to run this. And Python's like, cool. You know, so what happened here? Well, on line 1, I declared a variable called I and set it to 10, which is an integer. On line 3, I declared, and I set a new value to that variable, which is true, and then I printed it again, and that was fine. Let's try doing something like this in Java. Okay, so we're going to do the same thing in Java. We're going to say I is 10, and then we're going to print it. Yep. If I can type. Those of you who are impressed by my typing speed might notice that I'm also fairly inaccurate. So my actual words per minute are limited by that. Okay, so this is essentially, you know, and again, it's not a course on Python, and if you don't know Python, don't worry, we're not going to try to teach Python this semester. I just want to draw out this distinction between these two languages, which is sort of interesting. Okay, so this is a piece of Python code, and it runs fine. This is the equivalent piece of Java code, and it is not going to be okay. Java won't even run this piece of code. And the reason for this is, you'll see over here, this is kind of the one big difference between these. Obviously, we have system.out.println versus just print, so that's one difference. But the other difference is that when I declared my variable I in Java, I had to assign a type to it. I had to tell Java that this variable is going to store integer information. And so down here, when I tried to assign this Boolean literal to the variable, when Java analyzed my program, this program didn't even run. I want to be clear about that. We'll come back and talk about what exactly happens in these playground examples later. But this Java didn't even try to run this program because it detected a problem right away when it kind of analyzed my code before it actually started to run it. And the problem that it detected is that this variable called I that's declared to store an integer value cannot be used to store a Boolean value. So I can't change my mind later in the program and decide, oh, okay, I should really store, you know, a Boolean value and assign a Boolean to it. In Python, no problem, you know. So, you know, the analogy I used in the video that's in the walkthrough in the lesson is sort of like a container. So, you know, Python's containers are like a flexible bag that you can put anything in there. Java's containers are like a very, very specific shaped box that is only designed to hold a specific type of thing. Now, what's the trade-off? Well, flexibility is great, right? You can put anything in that bag, but when you go in there to pull something out, you have no idea what you're about to get. And so if you want to, you know, again, let's say I had a, I had a bag of stuff, and I basically told you, you've got to stick your hand in there and pull it out, and whatever you grab, you have to eat. Would you feel comfortable doing that? I mean, there might be some stuff in there that might not be very tasty, right? In contrast, right, if I had, I'm trying to think of like a container, like a fast food container or something that like clearly is designed to hold food, and I gave it to you and I said, okay, we have to open this, and whatever's inside of it you have to eat. You might feel more comfortable with that because you're like, okay, I'm pretty sure that, I'm not sure what's in here. Maybe it's pad thai, maybe it's a curry, maybe it's a hamburger, maybe it's whatever, but it's not going to be like a socket wrench, right? Or, you know, an extension cord or something like that, which is, you know, all the stuff that I could put in my more flexible container. Not a perfect analogy, but you know, hopefully one that's somewhat helpful. All right, so let me finish up by going back and talking a little bit about representation. Like I said before, getting computers to be able to work with data requires figuring out a way to transform that data to numbers, whatever it is, photos, video, the human genome, you know, weather information. We have to digitize it. I mean, if you look up digital and digitize, think about it, digit, right? It's turning things into digits, right? Digital is information that can be represented as a number, as a series of numbers. So we have to digitize stuff. We have to figure out a way to take whatever data we're talking about and convert it to numbers so that the computer can work with it. How we do that depends on the domain. There are different approaches for different problems. But I want to point out one approach because I think it shares a lot with the others, which is the ASCII character set. So text is an incredibly important type of information for a computer to work with. In about a week, we're actually going to talk specifically about how computers work with text, how they work with a data type in Java that we call a string, which is sort of another one of these types that's built into the language. It's not a primitive type, but it's built into the language and something that, I see that question, I'm going to get to it. Built into the language and something that we can use in our programs to represent text because it's so important, because text is such a big part of what it means to be in a human society, right? Humans communicate with each other through written language. As far as I know, I think we're the only creatures that do that. Other creatures talk to each other or communicate through vocalizations, but written text is so important, such an important part of what it means for us to have a civilization, right? So how do we do that in Java and other programming languages? So very early on in the computer era, somebody, I don't know who it was, sat down and decided on a convention that we would use to represent text within our programs. And this is a way of taking text and converting it to a series of numbers. And here it is. And you can see there are 127 different values in this character set. And they include, if we look here, kind of starting around value 48, they include the numbers. There's a bunch of different types of punctuation and mathematical characters, and there's the entire Latin alphabet in here. Now, many of you who come from other countries will note that there is a lot that this leaves out. And so I don't want to give you a sense that this is the right way to do things. It's not. Because there are thousands and millions of characters that you can't represent as part of this. In fact, there's characters that are used in common English, expressions that you can't represent in this, right? And so this is fairly limited, but this was kind of a first attempt at figuring out a way for computers to work with text. Now, we actually have much more sophisticated ways of doing that, including something called Unicode that essentially allows you to represent pretty much any writing symbol that anybody has created on Earth, you can now store in a computer. And in fact, I remember reading somewhere that so some of the Asian languages have quite a few symbols. And apparently there are some characters in the Japanese character set that are part of the Unicode standard that Japanese scholars aren't sure are real characters. Like, somehow they got in there and you can type them if you know how to do it, but they're not sure what they mean. So it's not clear exactly how this happened. So anyway, but this was an early attempt at doing this. And so I'll leave this to you. It turns out that, this might not make sense to you because you might say, well, why can I assign what looks like an integer value to a character? And the reason is because internally, Java is representing everything as an integer value. As a number. And so if you print this out, I'll let you try this yourself in the playground that's built into the lesson, see what happens, right? And then use this table and kind of see if you can get some other kind of interesting things to happen as you go. All right, so that's pretty much all I have to talk about. I saw a question pop up on the forum, which was a great one. Let's see. Yeah, float and double for floating point values, and then the difference between byte short and long. Yeah, so this is a great question. It's covered a little bit as you go through the lesson, so I'll encourage you to kind of dive into this. But the difference between these different types, so you'll see, and this is something that it starts to confuse people, right? Why are there 4 different ways to represent integer values and 2 different ways to represent floating point values? The reason, and this is not a course on computer architecture, and so I don't want to get too deep into the hardware details here, but the fundamental trade-off here is that in order to represent information, we need to take up space in the computer's memory. The more space we take up, the more information we can represent. For these primitive types, that means that there's a trade-off between the range of values that a type can represent and how much space it takes up in the computer's memory. So integers, for example, an int takes up 4 bytes. So that means, it takes up 4 bytes of space. You might have heard that term, your computer has, 4 gigabytes of RAM or, 128 gigabyte disk. That's the same bytes. Storing a single integer consumes 4 of those bytes. Now, integers have a certain range that they can represent. Let's see here. Does this go where I want it to go? It does. Okay, so let me pull up. This is really where I would go when I kind of needed help with this. Let me make the font a little bigger. I don't know why the fonts are so small in these Java documentation pages. So you'll see that an integer has a certain range of values that it can represent, and this is connected to how much space it takes up in the computer's memory. So the smallest integer that I can store in an int value is -2 to the 31. So that's about -4 billion. The largest one that I can store is 2 to the 31 minus 1, and that's, it's about -2 billion. The largest integer that I can store is 2 to the 31 minus 1. That's about 2 billion. 2 billion minus 1. In 2 billion in computer numbers, right? A computer 1,000 is 1024, right? This has to do with powers of 2. So if I need, now for most of our applications, that's a perfectly reasonable range of values, right? There's a lot of applications for computers that don't need to store anything bigger or smaller than those limits. And so for them, integers are fine. If you had an application that really needed to store massive values, and there are use cases for this, Java offers another alternative. This is something called a long. A long, integer takes up 4 bytes. A long takes up 8 bytes. So it takes up twice as much space in the computer's memory. But because of that, it can store more information. And so a long, you'll see I can store, something as small as -2 to the 63. I don't even know how to describe that as a number. It is really, really big. Well, actually, hold on. Let's see here. I think Google will be able to tell me. Let's put this in to, hold on. 2 to the 63. And it doesn't want to tell me what that is. Oh, come on. Just show me the number, Google. Yeah, it doesn't really, here it goes. Okay. Powers of 2. 2 to the 63, here it is. Okay, so this is the number. This is the, just let me zoom in a little bit here so people can see this. This is 2 to the 63. So that's millions, billions, trillions, quadrillions, quintillions. It's big. This is a big number. And so if I need to store something bigger than that, there are actually more options, but they're not built into Java. But this is the trade-off. So, some of the types take up more space, can store more information. Some of the types take up less space, can store less information. So for ints, for example, a byte takes up only 1 byte of computer memory, but it can only store 256 values. It stores from -128 to 127. You have to count 0. So if you total all those up, that equals 256 distinct values. The floating point types are the same. So there's a different trade-off, which I don't want to get into, that has to do with precision, right? So I'll just sort of show an example here. So here's this variable called temperature, and I stored this floating point value in it. But let's see what happens if I try to store a really small value. Let's keep going. It's 1, okay. That's still okay. Well, actually, hold on. Here's what we'll do. Yeah, forgetting how this works. Okay, so here's the problem with floating point values. You'll see that I stored a value that's actually 1 plus a tiny amount, but 1. And if I eventually go, there's going to be a spot where Java's good. There it is. Okay, so there's some point at which Java's floating point representation can store both the big part of the number and the little part of the number. But there's some point where I go past that, it's right here, where it only stores the big part. You'll see that that little part has been removed. Now, maybe you think this isn't a problem. When you get later into the program, you'll take some courses that will explain to you all the reasons why this turns out to be a huge problem. So you remember those stories about the spacecraft that crashed into Mars or whatever because they were 32 feet off with their calculation. this is the kind of problem that causes that, right? Because you think about it, I mean, that doesn't sound like a very big mistake, but when when you were shooting something from millions of miles away, you really have to be really careful, right? So these tiny little values turn out to matter. With a float, let's change this to a float, and you can see, now I have to put an F over here to go to float literal. Let's see here, now you're gonna see that the trade-off is at a different spot. So at some point, I can store the big part and the small part in a float, but a double allows me to store the big part and a smaller small part, right? So this is the kind of equivalent, sorry, I have to take this off. This is the equivalent trade-off for floats and doubles. So hopefully I answered your question. Boolean values, where do they get their name? From Boole, Alfred Boole, who came up with Boolean logic, right, which is a system for essentially making truth statements about things and using them to prove stuff. So that's where Boolean comes from, but it's really just a true-false value. You can think of it as a truth value, and Boolean variables and Boolean values are the core of how we make decisions in a computer program. So when you click on a button and something happens, maybe sometimes one thing happens, sometimes something else happens. There's a decision process in there that's going on, and essentially, if at some point the computer is going to say, okay, if this statement is true, then open this window. If it's not, then do something else. We'll cover this more later in the week. All right, I saw another question pop up there. Why is string not included as a type? Yeah, it's a great question. So string is not a Java primitive type. We will come back and talk about this. But one of the things I want you to notice, actually it's a great question, about the primitive types. Something else that's common about them. So one of the things that's common about them is they all store numbers or something that we can represent as a number. We talked about in the lesson about how you represent Booleans as numbers, how you represent characters as numbers. Where'd this go? The other thing about them is they all store a single value, right? So byte, short, int, and long, single value. Float or double, single value. Boolean, single value. True or false. Character, single character. I can't use a character literal to store more than one character. Let's try that. So let's try storing ziz as a character, and you can't do it. So I can store a single character, and that character can be anything in the ASCII character set. It's not going to allow me to store, see, that went wrong. When I try to store certain values, it's not going to work. But I can store any of the ASCII character set without a problem. And underscores and things like this. Oh, I have to be able to do it properly. But I can't store multiple values. And even if I put them in double quotes, I still can't store them. And so the primitive types have two things in common. All store numeric, something that is a numeric or something that can be easily converted to a numeric value. And they all store a single value. A string, if you think about strings, right, text consists of multiple characters. Text can be long, can be short. You could have a variable that stores a text message or a tweet that only has a certain number of characters. That variable could later store like the entire Constitution or the entire Library of Congress record for a particular thing, or like a really long book or whatever. And so strings in Java are treated a little bit especially by the language, but they are not primitive types. And we'll talk about why that is next week when we get to strings. Obviously, strings are a really exciting type of data to be able to work with in your program, and we will get there. Strings are also a good transition between these basic types of data that we're going to work with and Java objects, which we'll talk about in a few weeks, maybe about a month, right? All right, let me go check the chat. Yeah, so long values, you can use them. Most of the time when we do examples with integer types, we'll use an int. I would argue, if you're like working in your program and you're thinking, okay, I need to store some integer data, use an int. Later, if your computer is trying to run your program and it's running out of memory, maybe think about a smaller integer value if it works in your program. Or if you realize that the values that you need to represent are either really big are really big, then you might need a long. But an int is a good default. Same thing with the floating point types. A lot of programs by default will use a double rather than a float to start. And then if you need, if it turns out again you need to save space in the computer's memory, you can use a smaller type. One of the things that's gone on in computing, so Java is not a young language. Java goes back to, oh gosh, I'm supposed to know this, the 90s? Let's look it up. Let me see, go back to, Java was released in 93? Oh, actually Google's trying to tell me and I just didn't get it. 95, okay, yeah, May 95. So it's not a young language, it's a 25-year-old programming language. And you guys might think about all the stuff that's happened in computing since then. A lot of you weren't even, I should say a lot of you, most of you, many of you, almost all of you probably weren't even alive in 1995. I was alive in 1995. I'm trying to think. I was in high school. We had a computer. It was not a powerful computer. My phone is probably much, much more powerful than my computer was at home at the time. I think we were using AOL. Maybe some of you probably have never heard of AOL. AOL was a way that you could get connected to the internet, although the internet as it exists now was still something that was being formed. And so the biggest difference between now and 1995 is that computers are way faster. They are so much faster and so much more powerful than they were in 1995. They also have so much more memory. So I think the computer that when I went to college in 1998, don't you love these grandpa stories? I think my computer had like 32 megabytes, sounds right, of memory. I had a hard drive I had a 4 gigabyte hard drive. That was the disk drive in my computer. So, and that was like kind of a powerful machine at the time. That was 1998. So it was 3 years after Java came out. I remember I ordered, because I was collecting music, and I ordered an extra hard drive for my computer, and that hard drive was 20 gigabytes. And I was like, this is a big drive. My computer now, I think, has like 64 gigabytes of memory. And a hard drive that's like 256 or 512 gigabytes. So, and the processors inside it are also much, much faster. So, and this is something, that we have to thank ECE and the computer engineers for, because they built us these incredible machines. All to say that some of the concerns of a language like Java when it comes to storing data, an old language that was being designed and sort of being launched 25 years ago, are not as important now as they used to be. So I'm not saying they're never important, but I'm saying, right now, giving a lot of thought to which type of integer you're going to use in your program is probably not a good use of time, because, ints are fine. You could even use a long by default if you don't want to run into any problems. The computer can probably handle it. At some point, if you're storing like huge data sets, and like I said, the computer's running out of memory or your users are complaining because it's slowing their phone down, then you might start to think about optimizing. But the computers of today are so much faster and more powerful than they were 25 years ago, and that's really shaped the design of newer programming languages. And older programming languages like Java, some of the things that were important at that time just aren't as critical now. All right, another question. Get to that. It's a good one. Why don't you get an error when you declare a double variable but you initialize it with an integer? Okay, this is awesome. Great question. Let me see. Get back to. Okay, let's do this, and I'm just going to grab this. Well, let's grab this playground. Okay. So the question is, if I do this, let's see. Let's put 1, and I say, and I'm going to print that variable. So if I declare an int and I try to assign a double to it, if Java says can't do this, or I won't do it because I might lose information. So here's one thing about it. I've got a box for integers and I've got a double value. And in order to fit it into that box, Java is telling me that I'm going to have to like cut some stuff off, right? I mean, we talk about sort of fitting a square peg into a round hole. Well, when the square peg ends up inside the round hole, it's usually rounder than when it started. And so Java's warning me here that in order to do this, it's actually going to have to destroy some information. And computers do not like doing that. Now, let's look at the opposite. So let's say if I say a double and I initialize it with an integer, that works fine. Now what's interesting is when we print it, you see a decimal point that I didn't initialize it with. So why does this work? The reason it works is that there's no possibility that information is going to be lost here. That's what Java's worried about. You know, if I go back and, can I undo in here? Look at that. I can. So here, Java's saying, doing this is going to destroy information. And computers don't like to destroy information. In contrast, I guess I haven't figured out how to go forward. If I take a double and I put an int into it, Java's cool with that because there's no extra information that could potentially be destroyed. Integers, by construction, do not have a floating point component. And so putting them into a floating point container, it's like taking a round peg and putting it into a square hole, right? That's fine. That's going to work, you know? But the opposite doesn't. And so, what Java worries about, or what Java will warn you about, when you try to assign different types of literals to different types of variables, are cases where information might be lost. That's the thing that it's concerned about. As long as there's no possibility for information loss, you're okay. You can see that if you look at how characters work, right? So I can't use var. It's equal to 10, okay? Well, I have to use a better value here, okay? So this is, one of these fun examples to look at. So why can I assign an integer literal to a character? The reason is because internally characters are actually represented as integers. Now, this is a fun example because on some level this makes absolutely no sense, right? Like I took a character, I assigned an integer to it 55, and then I printed it and it printed 7. And I actually chose this one by accident, but it's kind of fun. And this is one of those ones where you could probably stump people and be like, what on earth is happening here? Until you look down at the helpful ASCII character table down here, and you'll see that 55 is the integer that corresponds to the character 7. So that's what's happening. I sort of gave away the fun part at the end of this. All right, so I've got a few minutes left. I'm going to do, if there aren't any additional questions, these were fantastic questions, thanks for asking. I'm going to do one more thing, which is I'll sort of preview a little something that we might use or introduce on a later lesson. And this is a new Java feature that is something that only came out a couple years ago. So let's look at an example here. Okay, so here's my integer declaration and initialization. And as I pointed out in the lesson, you can declare and initialize variables separately, but typically it's done together. So typically I have a statement that looks like this. A lot of times 0 is what I initialize it to, or 1 or whatever. And this statement does 3 things. It tells Java I'm going to use a number called big value. I don't know why it's called big value now because it's storing 1. It's of type integer, and I'm initializing it to 1. Now some of you may notice something about this, which is I've actually told Java the type of the variable twice. Okay? Why? Well, I told it over here. I had to declare the type of the variable. But then the thing over here is an integer literal. And when I'm assigning a variable, I'm assigning it to an integer literal. I'm kind of also telling Java again that this is going to store integers because the first thing I put into it is an integer. So you might wonder, like, this is kind of annoying. I'm essentially telling Java the type of the variable twice. And so I think this came out in Java 11, which came out a few years ago. Java now has a feature, and our playground supports this, although it's not included in the lesson yet, although again, we may get to this, where you can do something called, this is called type inference. So let's run this piece of code and see what happens. And it turns out that this works, right? And you can tell that big value is an integer because if I try to put a double into it, I'm going to get that error messages. And it's clear from the error message that Java knows that big value is an int. Now, if I set it to a character, you'll see the error message now says from double to char. So Java knows the type of this variable, even though I didn't specify it. Instead, I use this keyword that's new to the Java language called var. And so what var instructs Java to do is it basically says, figure out the type of this variable based on the initial assignment. So it says, okay, I'm declaring a variable called big value. I'm not going to tell you what the type is. I'm going to use this var keyword, which doesn't indicate a type, but I'm assigning a value to it right away. And so use that initial value to figure out the type of the variable. And so this is kind of like a small, type inference. So figuring out the type of something based on how it's used is actually a really powerful idea. And it's an idea that's behind the development of a lot of newer programming languages. Java is trying to get there. And this is sort of their first initial steps in that direction. Type inference in Java is not very powerful yet, which is one of the reasons why I haven't felt really compelled to kind of restructure the whole course and teach it that way. But it can be used for local variables. Now you might ask, can I do something like this? And the answer is no. Now, if I declare this to be a double, right, I can do this. It works fine. I can split the declaration and the initialization into two steps. But if I use a var, I can't do that. And the reason is that Java is using that initial assignment to determine the type of the variable. If I don't provide initial assignment as part of the declaration, it doesn't know what type the variable is, and it gives up. So again, this is why type inference in Java is not particularly powerful yet. There are other languages that would actually be able to figure this out. So they'd be able to figure out, okay, well, I can tell what type of variable this is because I can see that you immediately assigned it a double value, and so I'm going to infer the type to be a double. In Java, we don't have that capability yet. The language isn't quite there yet. So again, if you want to be, and you can use this feature in today's homework. Yeah, you can use it in your little programs that you write in the future. It works. It's part of Java. It's a new feature that was introduced as part of the language. Java has started to try to introduce some new features at a more accelerated rate over the past couple of years. And this is one of them that you might want to use. And you can use in your programs if you're a little, if you're lazy or indecisive and you don't want to type, int or long or double, you can just type var, provide an initial value, and everything will just work. All right, so I think I'm done. I think things as different size boxes is also a good way to think about it, particularly for the box analogy isn't perfect, and it's one of these things where I would kind of like use it as a mental model, but hold it at arm's distance because it's not a perfect fit. But it's not a bad way to think about it. Like if I have a really big number, right, it's hard to put into a little box. Now with floating point values, the problem becomes, numbers that have both a big part and a small part. The way, and you guys will learn about this in later classes, the way that computers work with floating point or decimal values is really interesting, super complicated, and not something that we dwell on in this class. But the way to think about it is, if the number is just really big, the floating point has no problem storing it. If the number is really small, the floating point will typically be able to store it. The problem becomes if I have a number that has a big part and then a really small part, right? Like we saw. So 1, if I just want to store 0.00001, Java can do that all day. And I can put almost as many zeros on the left side as I want. If I want to store 1.0000, now I've got a problem, right? Now because internally the floating point has to keep track of both this big part and the small part. All right, so yep. So hopefully let me check the chat to see if there's anything going on there. Is var and int the same? No. So var can be used for anything, right? So here you'll see that if I use var, I can store double, right? I can store a character. I can store a truth value. So var actually allows me to be flexible about what I put into this, as long as Java can figure out what type it is from the initial assignment. Again, this is a process known as type inference, inferring the type of a variable based on how it's used. All right, that's it for today. I will good luck with today's homework. Please approach us on the forum if you have any questions, and I will see you guys